In this lecture, we'll talk about some machine learning problems where knowing and understanding the past is very important if we want to predict the future. What are some examples of problems where past events are important? In the last section, we studied convolutional neural networks in a lot of detail. Convolutional neural networks work great with images, especially for image classification. Recurrent neural networks are a different kind of neural network architecture. These work great with text data and are typically used for sentiment analysis or text classification. They, of course, work very well with other problem sets as well, but text classification is one of the main use cases of recurrent neural networks. The basic building block of a recurrent neural network is a recurrent neuron. A recurrent neuron basically has state within it. It has the ability to hold some memory. The way recurrent neurons keep track of state from the past is by feeding back their output back in as an input. In addition to whatever inputs you pass into a recurrent neuron at a point in time, the previous output of that neuron will be fed back in as an additional input. Recurrent neurons are said to have memory or hold state. This ability to hold state makes recurrent neurons very well suited to learning time series data, such as stock prices over a period of time, and so on. We've already learned about the basic training process for a neural network. Neural networks are trained via optimization and back propagation. Training a recurrent neural network is slightly different. We tweak the back propagation algorithm. Recurrent neural networks are trained using back propagation through time or BPTT. In order to understand how recurrent neurons work, let's take a small step back, or rather, a pretty large step back, and see what the objective is of machine learning algorithms. Typically, y is equal to fx. There is some input data x, there is some function that is applied to the input data f, and you get the result y. The objective of machine learning is to basically try and find out what the function f is, given that you know x and you know y. Machine learning algorithms seek to learn the function f that links the features with the labels, the features being x, the labels being y. Let's take the example of a regression. In simple linear regression, you have some variable x, which is the cause or the explanatory variable, and this variable x causes an effect. This effect is the dependent variable. Now, because you know that this is linear regression, you've basically said that the function that links the features x to the output y is a linear function, and it takes on the form y is equal to wx plus b. If you're using linear regression as your machine learning algorithm, you're basically specifying up front that the function f, which links the features to the labels, is linear. The objective of the linear regression machine learning model is to find the best fit line via an entire training process, the line that best represents the underlying training data. We've already seen that linear regression can be learned by a neural network which comprises of exactly one neuron. This neuron just has the affine transformation, no activation function. The activation function is simply the identity function. Now, it's no fun with machine learning if all you're doing is trying to figure out linear regression. What you're really interested in is figuring out the complex function that links the input features with the output labels. Machine learning algorithms such as neural networks can learn or reverse engineer pretty much any complex function, provided that you have the right training data, which is labeled in the right way. Neural networks can figure out some pretty darn complicated things. We've also worked a fair bit with neural networks in this course. Neural networks are basically made up of layers of neurons. Deep neural networks have many layers. Shallow neural networks have fewer layers. Neurons in one layer are connected to the neurons in the layer that follow it. None of the neural networks that we've seen so far paid any attention to time relationships. But there exist problems in the real world, such as stock market prices over a series of days, where time relationships and data have special meaning, where learning the past and understanding the past is very important when you have to predict the future. Let's see some examples of cases where understanding and learning the past is critical to predicting the future. Finding patterns in the past will determine how future events will shape up. Let's say you want to assess stock market prices over the last week or month or year. This is data that you might use to determine whether stocks will be up or down in the coming week. Time series data or sequences are also important when you want to perform actions such as autocomplete sentences. Let's say you had a sentence like, the 2012 Olympics were held in. You can imagine that each word of the sentence comes in at a different time instance. This is when the user is typing this out on, say, a Google search box or on some other website. This is time series data, and understanding the past words in a sentence is important when you want to predict the next word. As another more cooler example, let's say that you're working with self driving cars and you have a particular car that has been moving in a parabolic arc at a particular location for the last 15 seconds. This data available from the past is important for you to determine whether that car is headed for a collision within the next 10 seconds or so. All of this data that you see on screen is time series data. Time values hold a special meaning here. You can think of all of these problems that I just described as basically a function which depends on past data to get new values. These functions learn the past. Now, these relationships where past values of the effect variable drive current values are called autoregressive functions. Notice in the current formula here that the past value of y of t minus 1 at the previous instant, affects the current value of y of t. All the neural networks that we've studied so far have been feed forward neural networks. Here, the inputs flow into a layer, the outputs come out of that layer, which flow into the next layer. Outputs are never fed back to the inputs. These are feed forward neural networks. The dense neural networks that we've set up and the convolutional neural networks are examples of these feed forward networks. Feed forward networks cannot learn from the past. They have no information about the past, they only have information about the present. And here is where lies the power of recurrent neural networks. Recurrent neural networks, made up of recurrent neurons which hold state or memory, have the ability to learn from the past. Anytime you see a sequence of data and you want to use that sequence to make some predictions, we are using past events. For example, if you want to predict whether the stock market will be up or down next week, and if you use data from the past week, past month, or past year, this is an example of a problem where past events are important. Or if you're monitoring a self driving car and you know the trajectory of the car over the last 10 or 20 seconds, you can see where the car will be headed in the next 5 seconds. Again, an example of past events helping us predict the future.